today we're starting section 12.6 on directional derivatives, and directional derivatives is what the second video is all about today. The first video we're going to do is all about the gradient, which is a tool that we need in order to calculate directional derivatives. All right, so the gradient of a function f is going to be denoted with this little upside down triangle, which, fun fact, is known as a nabla. But really we're just going to read that upside down triangle as the gradient of f. All right, so the gradient of a multivariable function is just the vector function that's filled with all the different partial derivatives that you can take of the function. So if you've got two variables in your function, f of x, y, that means that you can find the partial derivative of f with respect to x and the partial derivative of f with respect to y. Take those two derivatives, put them in a vector, that's what the gradient is. If you happen to have three variables in your function, x, y, and z, that means you can take the partial with respect to x, partial with respect to y, partial with respect to z, throw them all in a vector, and that's what we call the gradient. So the gradient's going to do a lot of things for us this semester, not the least of which is helping us to find directional derivatives and equations of tangent lines. But let's get some practice with these formulas and calculating gradients. All right, so here we have a function in two variables, f of x, y, and we're going to find the gradient. So I have a little reminder box down there at the bottom. So we're going to be creating the two-dimensional gradient vector where we have the partial of f with respect to x and the partial of f with respect to y. All right, so taking the derivative of f with respect to x, treating y as a constant. So derivative of x squared is going to be 2x minus y is the constant. So derivative of xy is just going to be y. And derivative of 2y squared will be 0 because y is a constant. All right, so my second component of the gradient, we're taking the derivative of f with respect to y. So the derivative of x squared is going to be 0. And with respect to y minus xy, we're going to take off that coefficient, which is the x. And then the derivative of 2y squared is going to be 4y. Okay, so nothing really new here. We're just taking partial derivatives with respect to the two variables and throwing them in a vector. All right, so let's try this on a function of three variables, which looks like a hot mess, but I promise is not all that bad. All right, so our gradient this time is going to have three components, one for each partial derivative of the variables present in the function. All right, so let's start off. This one's probably going to run off the page because it's so big. All right, so when we take the derivative with respect to x, notice that the only thing that has an x is the sine 3x, right? So the e to the minus 2z and the cosine 4y, those are just big constants that are going to go along for the ride. Okay, so I'm going to just blow through. E to the minus 2z is a constant. Derivative of sine 3x is going to be cosine. Leave the inside function alone. Need a little chain rule here, times 3. And then that cosine 4y is just another constant stuck to the function. All right, so let's keep doing that. So now we're going to do the partial with respect to y. Okay, and the only thing that's got a y is the cosine 4y. So the e to the negative 2z, sine 3x, those are just constants that we can copy. So e to the negative 2z times sine 3x, constants. Now we take the derivative of cosine 4y. Okay, so we're going to multiply by the derivative of cosine, which is negative sine. Leave the inside function alone. Chain rule, multiply by the derivative of 4y, it's 4. And that's the partial with respect to y. Partial with respect to z. So I'm not going to have room here. We'll move this down onto the next line. Again, only one of these three chunks of the function has each variable. So e to the negative 2z is really the part we're taking the derivative of. The blue and green brackets, those are just constants as far as z is concerned. So we're going to say, take the derivative of e to the minus 2z, which is, derivative, e is its own derivative. Leave the inside function alone. Multiply by the derivative of the inside function. So multiply by negative 2. Okay, and then the sine 3x, cosine 4y are just constants that we're going to leave going along for the ride. And that's my gradient. It's a little bit of a mess. I need to clean it up. So hopefully I can fit the simplified version all on one line. Okay, so in the first term, I'm going to pull that 3 up front. So 3 e to the negative 2z cosine 3x cosine 4y. My y component, I've got a negative coefficient on the sine 4y and a 4 at the end there. So I'm going to pull those up front as a negative 4 e to the negative 2z sine x sine 3x sine 4y. Okay, so again, I was just simplifying that whole term right there. We already did the first term, and now we're on to our third component, which was our middle line there, where e to the negative 2z, we took the derivative. Let's pull that negative 2 out in front. So negative 2 e to the negative 2z sine 3x cosine 4y. Whew, got it all in one line. All right, so that's our gradient. All right, so we'll get lots more practice calculating gradients. I want to go over to GeoGebra and show you one kind of neat thing that's true about the gradient. All right, so I have this GeoGebra applet linked on our Moodle page, so you can play along if you'd like. So it's got this kind of crazy function graphed over there on the right, and it's got a blue plane that's slicing through and creating the level curves of this function. So that's what you see over on the left. Those green curves are the level curves of this function. So that K slider is going to take that plane and slide it up, creating all those different curves. And then when you get onto the bumpy part on the top, you can see those level curves are kind of those two little circle parts. Okay, so what I'm going to do is turn on a point. Okay, and I can drag that point around A, you can see labeled over on the left, and I'm going to turn on the gradient of the function at that point. So you can see I can drag the point around, and GeoGebra is recalculating the gradient vector to the function at any given point. Okay, and its length changes depending upon where we're at, and it'll keep doing this for you no matter where you are. So you can slide up onto those higher ones, and I can slide this gradient vector around. All right, and the gradient vector does change in magnitude wherever we are. But one thing I want you to notice is that in every spot, the gradient is orthogonal to the level curve. Okay, you can kind of see that as we slide this around, and no matter where I drag the plane to, no matter which level curve I'm on, as I slide A around, you can see that all of these gradient vectors are orthogonal to the level curve. All right, so we'll kind of put that in our back pocket as the thing that's true about the special gradient vector is that the gradient vector at any point is always orthogonal to the level curve of the surface.